great student with whom I love to spend so much time, if I am not wrong, Tushar. So today we
Yes.
have a Tushar Makkar. He is an AI researcher and robotics engineer with over 12 years of experience in machine learning, computer vision, and reinforcement learning. He is a graduate of Department of CSE NITK Suratkal, and he has played key role in the early stage of AI startups and led AI chapter at multiple unicorns. He is currently building 10x construction, where he is developing AI powered robots to automate some of the complex construction tasks. So, welcome to this session, Tushar. And now, session is yours. You can go ahead.
Thank you. Thank you, sir, for this warm introduction. Uh, I'll try to share my screen.
Yeah.
So first of all, yeah, thank you everyone for joining this session. Uh, the main idea of this session, what I'm trying to do is I'm trying to tell you guys more about how are we using AI in robotics and how the journey of robotics has been from. So again, think of it like that robots have been there since like past 30, 40 years. And the algorithms which were initially getting used in robots versus the algorithms or the AI models which are getting used now. So there has been a journey. So I'm going to tell you about those nuances of how we apply AI in robotics. And what we'll do is we will start uh, by taking an example. Uh, Mostly what I have done is I have given an overview of most of the techniques which we use, and I can go in technical depth in each any one of them. But to keep the session within the reach and make sure that it is understandable by everyone, I have kept it a bit on a higher level. So yeah, maybe what I'll do is I'll yeah. So there's a brief intro about myself. Graduated from NIT Suratkal, Computer Science 2015. Worked at Google Research. I was initial members at a couple of startups. So one of them is Rivigo, then AI. Like I was the first AI engineer, grew the entire team. We had essentially I built the Bangalore office and Noida office from scratch. And during the journey, uh, essentially was mentoring roughly around 50 people in the team. And I have worked on different domains, one of them being computer vision, reinforcement learning, NLP, again, LLMs, VLMs. Most recently, I've been working with vision language action models, which I'll share briefly more about those things. I have roughly around like 20 plus patents in the domain of AI on my name. uh, yeah, happy to meet you guys, and let's actually deep dive into. Again, I have tried to keep this a bit like a informal session. But yeah, again, so as you guys can see, there is a huge expectation and reality match, and that's the reason why we can't see robots daily, basically in our day-to-day life. Okay, people on one side, we have all these research labs doing a lot of cool work, but still now the robots are not omnipresent because the intelligence has not evolved to the level. And that was the base hypothesis with which we essentially started building 10x construction. Because of all these AI models, now robots can essentially work in a lot of unstructured environment. Earlier, people used to use a lot of classical computer vision or classical robotics techniques to do it. But now all those classical techniques, because there is inherently the problem with classical that they are rule based. If you can't codify a lot of rules, it becomes very difficult to essentially build on top of it. Okay, and for unstructured environment like maybe in your home or on the roads, it becomes very difficult for it because it has not seen a lot of those cases. And adding heuristics on top of each other is not the solution. So what we will do is we'll try to essentially have a general purpose problem statement. So let's say if you have to make a warehouse robot, okay, how will you essentially make it? So the scenario is something like that. So there is going to be a mobile robot. It will essentially navigate autonomously. Okay. There will be these aisles of inventory shelves. And think of it that this robot is at maybe a warehouse like Amazon's warehouse or Flipkart warehouse. Okay, it should autonomously navigate through those shelves while avoiding collision. It should figure out where the some specific products are present, and if possible, it should pick those products and transport it from one place to other. Okay, this warehouse robot, it will operate in a semi-structured environment. Like basically think of it like the warehouse map remains same, but it is dynamic. What I mean by dynamic is like although the floor layout is known, there will be obstacles like people or other robots coming here and there, and they can come unpredictably. Okay, so although the map is known, still there are some basically some sense of dynamic dynamicity associated with the robot. Okay. Now, how do robots know about the world? Because it's just a piece of our hardware. So for it to know about it, there are different kind of sensors which we use. So some of the sensors are like LiDAR. So LiDAR is known as light detection and ranging. What it essentially does it kind of throws light signals and it receives it. And based on the time which the light takes to receive, so it figures out how much is the distance. So think of it like we have this velocity. Basically, we know the velocity of light, we know the time. Now we can easily compute the distance. So this is a LiDAR. So based on LiDAR, you can essentially get very precise measurement of the distance of the objects, also on a depth also. Okay. And then there is depth cameras. So depth cameras work on a similar principle. Again, they are like you can see the RGB and D is based on the IR sensor. But IR sensors generally they are not very precise compared to LiDARs. Okay. Then there is safety sensors. So what safety sensors? They are mostly like very precise ultrasonic type sensors. As soon as you are very close to them, so they don't work on a very large range. They work on a very small range. Think of it, the small range can be let's say a meter or something like that. So as soon as you cross or you are in that range, but they are very precise. Like you will know at the same moment when a person is coming or it collides with that. Okay, and it tells the software and the hardware to stop. So these are like safety sensors. Then there is IMU. IMU is known as essentially inertial measurement unit. So what it does is it has three main components. One is accelerometer. So accelerometer essentially tells the acceleration. Basically, which direction is it moving? Then there is this gyroscope. Gyroscope tells the orientation. Basically, angular velocity. Basically, are you moving and which direction, which axis are you moving? And the third is the magnetometer. So magnetometer, think of it, it's like a 3D compass. So you can tell like where exactly is the north, where is the south, west, east, all those things. And GPS. So to figure out the approximate location of the robot. Yeah. Now let's talk about the main challenges which you might see in these kind of robots. So since the problem to navigate autonomously, pick up objects, it's a complex and multifaceted. The robot needs few modules. So one of the module is perception. So it needs to figure out where it is and detect the objects. Then you also need to do a planning because it needs to figure out like right now it is at a point A, it needs to go to point B. So how should it go and travel to that point? Okay. The third component is navigation and control. Basically, once it decides the path, once it plans the path, it needs to move along that path also. There should not be deviation along that path. Okay. Then fourth is the manipulation. So it will grasp items. It will basically figure out how to pick it up because again, each object has different density. So the robot needs to be very self-aware as it like how a human does it. So let's say there is a mobile, you will pick it like this. But let's say there is a water bottle, you need a bigger grasp. And for picking up mobile, you might apply different kind of force on the mobile versus a glass. Because let's say if you are putting a more force on the glass, it might break. So it needs to figure out all those things. And these robots should achieve high reliability and safety in these kind of environments. For example, they can't crash into workers or shelves. Okay. And let's say they figure out that a path is blocked, they need to quickly reroute. Okay. They also need to accurately identify the correct inventory Maybe they might use things like computer vision to scan barcodes or recognize items and also coordinate with other robots. Okay. So meeting these different challenges, so you can essentially do this in two ways. So one is the classical, and we will teach about both the things, the classical as well as the AI based way. But again, so all these problems are non-trivial, okay, and they require high degree of algorithm design. So in general, the base behind classical robotics is very simple, okay, and in general, the principle is very simple: sense, plan, act. Okay. So first of all, robot need to sense the environment using the sensors which we discussed. So for example, it will figure out the wall is like 4 centimeters away from me. Then it needs to plan. So it will figure out, yeah, that this wall is very close. Maybe I should move a bit away. And the third is act. Okay. So it will move a bit away. It figured out whatever it planned and it acted on that. And again, based on that, now it will again do the sense. It will say now it is at, let's say, like 5 meters. Now I am comfortable. Okay. So the entire robotics is essentially built around this sense, plan, act, and loop. Again, sense, plan, act, and loop. Okay. Now let's talk a bit about the different components as we discussed. So one is the mapping and localization. So first of all, it needs to create a map of the warehouse wherever the robot is. Okay. So there are multiple techniques which you use. So one of the technique is known as SLAM, which we will go in a bit of details. Then there are these things like Kalman filter-based sensor fusion to build maps and basically locate the robots. Then the next thing is it needs to plan the path. For that, we can use algorithms like Dijkstra, A-star. I think this though everyone would have read or know about these things. As well as there is sampling-based planners. So you essentially basically you have some points, then you approximate the distribution, the density of the distribution, and based on that distribution, you figure out what is the plan you need to make. Then there is this motion control. Again, I think people from electrical and electronics background would know about there. This PID controller. Based on that, you figure out are you at the right position. If not, you essentially correct those positions. And then the fourth and most important part is the perception, where you use different kind of classical computer vision algorithms like edge detection, template matching, so on and so forth. Okay, cool. Let's talk about Kalman filter. Again, I think Kalman filter is also a very common, I think, thing which most of you guys would have knowledge about. So think of it like that. So basic idea is what Kalman filter does is, given the current state, it makes a prediction. Once it makes a prediction, it also gets the measurement at that particular point, and then it figures out the optimal way in which you will merge the current measurement and the prediction. Okay. So for example, you have an estimate at k-1. Okay. You will predict that in, let's say, okay, let's talk about this example. Let's say you know the velocity with which the car is moving. Okay. Based on that velocity, you figure out that it is like 2 seconds, and let's say the car is moving at, let's say, 10 meters per second. So since it is 2 seconds, this means the car might have moved at 20 meters. So you know that the prediction is 20 meters. Now you will also know, based on the, let's say, last time when you made, let's say, the prediction, the car, instead of moving 20 meters, it moved at 18 meters. Okay. Now you know there is 20 meters and 80 meters. Now you need to merge these two values. And let's say when you merge these two values, you figure out that 19 meters is the correct answer. So that's the basic intuition behind Kalman filter. You make a prediction, you get the measurement, and you essentially weight those measurements. Okay. So generally, Kalman filter in general is a linear, basically, based thing. So think of it like that. A Kalman filter can merge different sensor data. For example, it can merge the IMU data, wheel odometry data. So wheel odometry, I'll just explain you quickly. So wheel odometry is essentially the number of rotations the wheel of the robot moves, and based on that, you know the diameter of the wheel. And let's say it made one complete rotation. This means the robot would have moved by the diameter of the wheel. So you get that value also. And again, LiDAR, so I have told you. So it can fuse the values of IMU, wheel odometry, and LiDAR to get a more accurate estimate of the robot's pose than any single sensor. So what you can do is, you will know the prediction from wheel odometry, you will know the prediction from IMU, you will know the prediction from LiDAR, and you can easily merge all of them. However, this approach works under the assumption of known noise distribution. So you assume that there is some noise, okay, and or what you also assume is that all these different models, they can be linearly combined together, okay, and the parameters which you need for combining them. So most of the parameters, so Kalman filter predicts some of those parameters, but then there are some of these things, the KP, KD values, which you might have to fine tune and pick yourself. Okay. For example, you will use some rule based and hand tuned parameters to figure out things like what is the noise covariance and how much trust do I have on the particular sensor. Okay. Then comes the mapping and localization and SLAM. So SLAM, the full form is like simultaneous localization and mapping. So think of it as a robot is there in a particular location. So it will move, and while moving, it is also observing the space based on these different sensors. And based on this observation, it you can essentially extend the map. Okay. And because you're extending the map, let's say you come back to a particular position, you will figure out what is the error which your model or the SLAM model gives, and what is the current measurement value. And you can only minimize those things. Okay. So basically the idea is the SLAM is used to estimate robot position on a predefined floor map and create map. So it is essentially creating the map, as well as it can basically localize the robot itself. So as you can see, so in general, so this example is like visual odometry based SLAM. So you have input from camera and you have the input from the wheel odometry. Basically what I told you about how much the wheel is moving. Okay. So you have an image sequence, you extract some features, then you essentially do based on the feature matching, you'll figure out how far the robot has moved. You do some kind of depth estimation, and you get based on the feature that earlier the robot was at this location, now the robot is at this position. This means that the the robot has moved by this angle. Similarly, you will get the odometry based responses also, and you will figure out that at this place the robot would have moved at this angle, and then you essentially merge those values and you do a local approximation based on that, and you will figure out here this is the current map and approximately I'm at this location. Okay, so this is the basic intuition behind SLAM. Then we were telling about motion control. So again, so this is also a very common concept. So what you do is, so this is another PID control. So P is like proportional, integral, and derivative. Okay, the basic intuition is P tells right now how much is the difference from the current, like let's say you predict a value, what is the difference from the current value. Okay, then second is it also takes the past difference, basically how much the robot, how much error is it accumulating in the past. Okay, and then D is essentially like it predicts the future difference. Okay, so think of it like that. So term P is proportional to the current value of the robot and what is the error it is getting. For example, if the error is large, the control output will be proportionally large using the gain factor Kp. Okay. Similarly, term I accounts for the past values, and you integrate them over a time to produce essentially the I term. So think of it like that. Let's say in the past, if the error was huge, so it essentially like you will have that I value large. Okay. So what this essentially tries to do is this will result in a proportional effect diminishing as the error decreases. But this is compensated by the growing integral effect. Okay. And D is more like a future thing. Okay. So it is the best estimate of the future trend of the error based on the current rate of change. For example, let's say you know the currently it is essentially moving at a particular value and this is the error which is happening. So it essentially predicts. So this is more of an anticipatory control mechanism. So it effectively tries to reduce the SP minus PV error by exerting a control influence generated by the rate of error change. Okay. So one thing is more like integrating the past errors, one is the current error, and one is what is going to be a future error. So this can only dampen this out. So if you see over here, so you can see like how the error and things changes when you change the value of Kp, Ki, and Kd. Okay. So KD is like it predicts the future thing. KI is like the past errors. KP is like the current error. So KP is essentially trying to make it to one. Okay. And when we say KI, so KI is essentially trying to basically the past, whatever has happened, accumulated, it is trying to reduce that. And KD is predicting the future. And basically combining all these, you can essentially get a very good motion control system. Okay. Path planning, again, I think Dijkstra, we know A star is like just an extension of Dijkstra. It's like a best first search. What it does, it always picks the node with the lowest estimated total path cost. So as you can see over here also, so what it does is, so there are two components. So Dijkstra has only one component. It has two components. One is so think of it like there is f of n. The function is equal to g of n plus h of n. So g of n is like a exact cost from the start to the current node, and h of n is the heuristic guess of the cheapest cost from the node to the goal. Okay, and if think of it like if h of n is 0, you will make a Dijkstra algorithm. If g of n is 0, you will make a greedy algorithm. Okay. In general, these algorithms help us to output a collision-free path or waypoints so that you can avoid a static obstacle. So let's say in the map, you will know like there is an obstacle at a particular point, the robot knows about it, then you will essentially make the cost of that particular node to a bit high, and that's how you will figure out what is the lowest cost path. Okay, cool. So yeah, in the classical computer vision for the perception side, so what people essentially do is, so they have these edge matching algorithms, as well as they have these things on the apparel tags, using those kind of or QR codes, so the camera can essentially detect those and figure out where exactly it is. Okay, so it might not need to remember the things. It can just scan the particular QR code on an apparel tag and essentially figure it out. So, for example, in the warehouse robotics, how it is used is people identify the correct item or bin or the shelf based on these vision cues or markers. So they just need to figure out whether it's a color tag or read a barcode and do some kind of image processing. You can use classical techniques like edge detection, template matching, and since the lighting is also uniform, you can essentially use those things. Uh, for navigation, also people use it. Like people basically lay lines on the warehouse, and it figures out there key where exactly, how exactly it needs to move, and it tries to move within that. But again, think of it like that. Let's say for a system, something like an ADAS or like a autonomous driving, uh, you won't have these things. So that's why autonomous driving took so long, whereas warehouse robotics was like solved like 10, 12 years ago. Okay. Now there are some very interesting techniques also. For example, there is this shift. So shift is known as scale invariant feature transform. What it tries to do is, let's say you are seeing a particular thing which is like it's a template matching thing. So let's say if there is a huge box and then there is a small box, because when you move away from the place, so initially we'll see like when you are very close up, you will see the box to be huge. When you keep moving away from it, it will start becoming small. So all those things you essentially can achieve via SIFT. So SIFT was a patented algorithm till 2020. After that, the patent got expired, and now people use it literally a lot of things. So there is a SIFT and then there is SURF. So both the algorithms are pretty good. So what are you essentially doing? You do a Gaussian filtering, you subtract, you basically scale it up, scale it down. So there is a downsampling and scaling up is needed, and then you figure out the key points. And based on that, you make essentially dual hierarchy based thing. And for example, if you see in this Indian rupee picture, you can essentially figure out where one part is there in one image versus second image. So you can essentially make those lines. So yeah, cool. So that was a bit about the classical approaches. But as we discussed, so there are these some of the limitations of classical approaches. Okay, as it is also being shown over here. So they excel in like well-structured settings where accurate models are available. But the behavior in general, the good part is that the behavior of classical robot is highly predictable and verifiable. Like if there is no uncertainty basically involved in it, because it's not a probabilistic base, it is very deterministic. Okay, which makes them very crucial in safety critical applications. For example, let's say manufacturing or medical robots. So think of it like that. Let's say a robot is performing a surgery, and because of incorrect lighting, it does something wrong. So for these algorithms right now, because most of the like algorithms in the AI, they are not robust. So people mostly use classical algorithms for most safety critical applications. And again, and the basic reason is also this: like decades of research, they have made this algorithm very robust, and they achieve a very high precision and reliability, but only in the controlled environments. Think of it like that. Let's say if the environment is not controlled, okay, so it becomes very difficult. So think of it like cases like there are these dynamic or unstructured environments. Okay, classical robots rely on predefined maps. So if the environment changes in ways which is not pre-coded in these models, it breaks. So think of it like that. Let's say if if a robot is moving, whereas robot is moving, and there is a pallet which falls, okay, and classical planner doesn't know how to cope with it, so it will just break. Okay. The other issue with this classical approaches is the scalability and complexity. So as you keep on adding different heuristics to it, it becomes difficult to scale. Okay. Every new scenario might require new rules on models. And for like again, for example, extending the wearer's robot to not just navigate, but also to pick. Okay. And picking also will depend here what type of object is it picking. Is it picking uh, air conditioner versus is it picking a mobile versus where it is picking a cotton roll. So you need to keep on adding all those things. So it becomes difficult to scale. And again, they do require a lot of manual tuning. Okay. And because of its limited perception capabilities, it can't basically figure out things. So think of it like that. You need barcodes each and every way, which is essentially very cumbersome. So let's say you tell the robot to pick uh let's say pick a chocolate. uh, Now, right now, it might not know the difference between picking a dairy milk chocolate or picking a maybe a munch chocolate or a perk chocolate. Okay, so we need to essentially train those models, train those classical algorithms across different things and making sure that it essentially scales accordingly. And because these pipelines are in general modular, uh, but still because of these rules, it becomes very difficult to integrate a lot of rules together. Okay, which causes a lot of failure in real world scenarios. Okay, but again, for a very controlled environment, this is the best. But when you essentially have a uncontrolled dynamic environment, this doesn't work out. Okay, so then what is the alternative? So because of these approaches, so think of it like the past, like till like past 5 6 years, robots are very limited to very small, like small use cases. But now, because of the basically advent of AI models and improving the capability of the GPU processing and all those things, and the models have also, you can train a very deep model. Now you will start seeing robots essentially being omnipresent. So again, so my hypothesis is in another 10 years we will have more robots than humans. But let's see how it goes. Cool. Let's now we'll essentially start talking about the deep learning based methods. So we talked about Kalman filters, where you can essentially take different basically modality of data. Let's say once you have lidar scans, you have cameras and other things, and then you essentially make a linearized equation, mathematical equation, and those equation you'll need to maybe know what is the variance of the noise and all those things, and then you essentially get the parameters for EKF or the Kalman filter. But over here, you don't need anything. So what you can basically, what deep learning offers is a learned approach for fusion. Fusion means that you have different sensors and how can you merge the data. Okay. Where the robot can figure out how to combine sensors just by training on the data. So you don't need to tell your how much weightage should it give to the lidar value, how much weightage should it give to the camera value, how much weightage should you give to the IMU value, all those things. It can just figure that out on its own. So instead of hand tuning weights, we train a neural network on sensor inputs to predict some outcome. Okay. And the network can then implicitly learn the sensor weighting and their nonlinear relationship. For example, let's say a deep network could take an input as a camera image and LiDAR scan and output a rich understanding of the scene. Basically, the embeddings you can figure out. And then basically it can itself learn to trust the LiDAR value because it gives a very precise distance, but it learns to trust camera for object recognition because again LiDAR doesn't have the vision capability, so it uses more of a, think of it like LiDAR for distance and cameras for object. Okay, now this can happen in two ways, so that's what I have mentioned. So one is the early fusion, where what you do is you feed multiple sensor streams into the first layers of the network together and then let it predict the final thing. Or late fusion, where what you do is you essentially have separate neural networks for each one separately, and then at the end you will fuse them together. Both of them essentially works pretty well. So I think the example which I have taken here is like self-driving cars. So it fuses radar data, lidar data, and camera data uh, for better pedestrian detection. So basically, you can't miss a pedestrian. Like even 1% is like bad. Okay, and you and again, so in the warehouse scenario, we can think like it can combine the reading of maybe RFID reader along with maybe the distance of the particular thing, uh, and let's say in case something is occluded or something it can't see, but based on the RFID it can figure out whether it is there or not. So it can essentially figure out and improve its position based on these kind of sensor, like deep learning based fusion methods. Okay, and this is just a very brief basically telling you what all are the main major differences. So in the classical fusion, the model type is like fixed mathematical. In the deep learning, you learn from the data. How, like the larger the data, the merrier. Again, all the classical methods, they have limited adaptability. In the deep learning, you have very high adaptability. The complexity handling in the uh, classical methods, again, it can't essentially model non-linearity. Versus in deep learning, it can handle any kind of complex relationship. Again, data, you can essentially train a classical model or just build a classical model with very limited data. Okay, because you are making explicit models. But for deep learning, you need a lot of training data. So that is a limitation for sure. And the worst thing is the interpretability. Like most of the classical methods, they are very high interpretability and they're deterministic. For deep learning uh, based fusion methods, so the interpretability is low, and in general, it's most of a black box kind scenario. Okay, cool. Now let's also talk about how we do perception based essentially in deep learning. So again, so using these deep neural networks, particularly things like convolution neural network, like CNNs or vision transformers. So vision transformers again as a concept evolved in like past 6 years or something. Uh, Robots can now interpret camera images or other sensory inputs with human-like recognition abilities. For example, a deep learning model could take the robot's camera feed and identify things like obstacles, humans, and specific products on shelves via just the object detection or image survey. You don't need to essentially. So there are these general purpose, uh, basically vision transformers, which can essentially detect anything out there and segment a lot of things. Okay, so again, so CNNs, I think most of you will be aware like how CNNs work. There's this convolution layer, and you basically merge the values and all those things. But vision transformers is again a comparatively newer. So CNNs have been there since like past, I know what, like 15, 20 years or even more than that. But vision transformers as a concept, they recently, there was a very uh, beautiful paper, which is like an image is worth 16 dot 16 words or something like that. So, but the basic intuition behind it is like you treat an image the way a language model treats a sentence. So what you essentially do is you split an image into fixed size patches. Then you embed each of the patch into a vector. Okay. And then you basically add some kind of positional encoding. Positional encoding, I think transformers, you just understand like what positional encoding is. But yeah, in general, the idea is it figures out where it is with respect to the other words. Okay. Then what you essentially do internally is you feed the sequence to a standard transformer encoder, which let every patch attend to each other patch. So there's this thing known as self attention. So this global self attention makes the network look at the whole picture from the very first layer instead of building up locally, like step by step. So in CNN, you essentially do step by step thing. Over here, it can essentially do basically self attention. So it has different patches, and one patch it figures out how it is related to the other patch is related to how other patch, and so on and so forth. Okay, this is the basic intuition behind bits or vision transformer. And again, so in perception also, as we were talking earlier, you can essentially use depending on the modality of data, you can use train different kind of networks. For example, you can train a point cloud based network. So point cloud is the output which lidar gives. So it gives different points, and those points essentially represent the distance uh, of the particular obstacle of a particular thing with respect to the robot. So you get the point cloud, then you make a feature embedding out of it, then you make a super point graph, and then essentially you do a point wise labeling like what is this, what is what. Okay. Then there is voxel based thing. So the difference between point cloud, so point cloud is points. Voxels is like a cuboidal structure. Why we use voxel? The basic intuition behind using voxel is because point cloud might not be uniform. Basically, the density of each of the points might be different across different areas. So what you do is you essentially kind of figure out here in a particular location if the point of density is that point of density is above a given threshold. So you make a voxel out of it. Okay, and the size of the voxel can be different though. So you essentially make these voxels, and now instead of point clouds, what you do is you train your feature embedding on the voxels. Okay, and then there are these different specific models for figuring out the embeddings for the voxels, and then again essentially the output will be the same, which is the point wise labeling, because eventually you will figure out that this voxel corresponds to particular this thing, and then that because you know what that voxel is corresponding to in the point cloud structure, you can essentially map it back to the PCL or the point cloud. Yeah. And the third, which is again very common, is you can just directly use the images. Okay. So for example, you have different images, and then again you can use things like vision transformer to get the feature embedding. Uh, and then you can have again there is RGBD. You can have a depth layer also integrated. And again at the end, because the depth layer is integrated, you can again do a point-wise labeling. So there are different approaches to do the same thing, and you can essentially combine all these approaches also and figure out which works best. But again, the combining approaches, the only issue is the deeper the network becomes, the more data hungry it becomes. So you need to be a very you need to play the devil's advocate kind of thing, like whether you need to increase the data or whether you need to increase the size of the model, and what is the time complexity and all those things you need to take care while you essentially train these models. Cool. This is the pretty interesting paradigm which is shift is happening. So again, it is more on the basis of reward penalty based mechanism. Uh, yeah, you take a robot, you get it in a particular space, and you tell doing this is if you do something like this, you will get a reward. If you do something like this, you will get a penalty and you'll get penalized. Okay. And right now it is getting used in robotics like anything. Okay. So there is this thing known as reinforcement learning based control. So as we were talking about the PID based control, now things have moved away from reinforcement from PID based to RL based control. Okay. Now the basic idea which I just told you, like you need to do a decision making. Okay. And there are multiple ways to do the decision making. Okay. One of them is the reinforcement learning. Okay, then there is another idea which is known as imitation learning, which we will also discuss in some time. But yeah, so what you do is instead of writing a planning algorithm, we can train a neural network policy by reward and trial and error. So you tell you try these things and 10,000 times and do it randomly. And wherever you do it in the correct way, I will give you a reward. If you do it in an incorrect way, I will give you a penalty. Okay. So for example, the robot could learn to navigate by being rewarded for reaching targets quickly without collisions. Okay. And when you train that over many training episodes in simulation or real warehouses, again, the problem is you can't do RL on real world. Like it's very difficult because let's say if you are trying to do RL on real world, it might just break the hardware. So generally, what people do is they train it in simulation. Okay. And right now there is a huge and beautiful simulation tools. So there is this thing known as Isaac Sim. It is a tool by NVIDIA. You can use Isaac Sim along with Isaac Lab combo to essentially simulate the robot behaviors. Okay. So what you can do is you can make a deep RL based algorithm which can discover efficient navigation and uh, and the beautiful things about these things is here it can even find unconventional ways which a human programmer might not have ever considered. So think of it as, let's say if you want to go from point A to point B, you can, or let's say if you ask someone to basically touch your ear, a human is like he will just always just like this because we feel this is the most optimal. But maybe because of some scenario or a reward kind of thing, you can essentially touch your ear like this also. But a human might not have coded it like this. But now because RL is just trying a lot of variations, it can actually figure out unconventional ways and it can figure out it in a better way. So generally, deep RL has shown a huge success in the robot manipulation task, where, for example, like a robot learning to open doors or grasp some objects through many trials. For example, this is one other case where we can use essentially, let's say if there is a screw and there is a nut and you want to put the screw on the top of nut. So it needs very precise figuring out multiple things. Like you need to figure out okay, how much closely you want to pick, what should be the force, what should be the where is the screw located, and when should you drop the thing. So all these things, the entire policy is being learned by RL. So yeah, again the current RL algorithms, essentially the way how you train RL, you can essentially make a robot learn a new thing in just a few hours of practice. Because in simulation, let's say you can run tens of thousands of same robots, and now because in each second there are 10,000 iterations which is doing, so it can figure it out in the optimal way, as well as the algorithms have also improved. So there are different algorithms. Like for example, there are very famous optimization technique like proximal policy optimization (PPO). So even the GPT, the initial version of GPT, like GPT-2 uh, onwards, and even I think GPT-3 was also using. So they have this RLHF. So over there they used to use PPO, like proximal policy automation. The basic idea or the intuition is you basically move the policy one direction and the delta needs to be very less. So think of it, you just nudge the policy to move in the positive reward, but don't just force it. Okay. Now after that, I think there have been a lot of improvements. Again, PPO is easiest to train. Like there is other RL techniques like DPO, which is known as direct preference optimization. And the basic idea is like uh, instead of moving it slow, what you do is you use basically any result, you say that it is either a yes or no. So you make it a classification problem rather than an RL problem. And based on the result of the classical problem, you essentially try to train the RL policy. So that is the other DPO which got very popular. Now again, things like DeepSeek happened. They have this GRPO and all those things. So it's like group relative preference optimization. Again, you essentially do it in a group by group manner so that it learns in a much faster way. Uh, and again, so there is a very another popular thing known as soft aggregating SAC. Uh, what it does is key it pushes you towards the right solution, uh, but you can still move back to the older solution because the best solution might essentially be the previous one. So think of it like that. The basic idea is like you can be successful, but you can still keep your previous options open. So that is the basic intuition behind RL and how it is getting used in the robotics. Uh, Now, again, so instead of thinking, so over in the classical models, what we feel is what we do is we have different steps. Like you have this sensor fusion, you have this SLAM, then you have this perception module, then you have this motion control module, then you have this navigation module, then there you have manipulation module. Okay, you have lot of modules. Okay, now there is this new trend which is coming, which is the end-to-end system by using deep learning. So just give me a minute. So what you do over here is you essentially you try to make an end-to-end model which can do entire of the thing without having any basically modularity in between them. So for example, you can train an end-to-end navigation model. So there is this thing known as imitation learning. So imitation learning is really uh, you wear a suit of sorts and you tell it here really move this from this to this, and you take the sensor values and you tell ki if this kind of thing will happen, you have to do this. If this kind of thing will happen, you have to do this. So you can essentially use imitation learning. You can use the reinforcement based learning, as well as you can have these classical algorithms. But you combine all of these things into a one basically module, and you generate a lot of data set from them. And once you generate the lot of data set from them, that entire data set is what you use for training your downstream, the end-to-end machine learning system, which takes in the outputs from the imitation learning, output from the RL kind of thing, and custom neural networks. But what it does is the input to it is different kind of different modularity of what do you say data, and what it essentially outputs is the final result. So you don't have to worry about creating a map, whether it is moving at one map place or not, whether it is perceiving it correctly. It's just that based on the input, it will give you the final end-to-end output. So that is what it is doing. And now a lot of people are trying to use it, but yeah, it's a very again a newish or like cutting edge thing which is happening. Cool. Now let's talk about VLMs. I think a lot of you, like everyone would have heard about LLMs, large language models. So this is one level extension to it, which is a vision language models. Okay. The basic idea behind the vision language model is you will get essentially images, and you will have the reasoning of these language models. Okay. And on top of that, you will figure out what is there and how to get it done, and then the robot will do it. Okay. So for example, like VLMs serve as a bridge between high level reasoning and low level control. Okay. So there is a very famous paper, again, research paper from Google, known as Say Can. What people do is they use LLM with visual perception to do action based reasoning. So for example, Say Can, what people do is they use an LLM to interpret a user's request and figure out a feasible sequence of actions, and a vision system, which is the VLM, like vision plus LLM, to execute them. So the vision language understanding told it what it is saying and what the user wants, allowing planning to happen in a much more like semantic way. Okay. For example, let's say a person might have said that, let's say, pick up the chili or whatever is being shown over here. It figures out there what it is need to be done. It creates a plan for it, and then essentially does it out. Okay, so this is not pure learning or pure classical. It is using a learned, pre-trained large language model or vision language model to guide the classical robotics based thing. So for example, how it was like you train it by different human videos, and there is this robot execution which happens. So there is this VLM which sees what is happening. It selects the keyframe. There's a visual perception, and then there's this language model, and from that it essentially creates a plan. Like you have to do, first of all, let's say pick up the eggplant and drop it in this. Pick up this thing, do this. Pick up this thing, do this. Pick up this thing, and the entire thing is now. So there is no motion control attached. Okay, so you essentially say ki yaar, you tell that robot joint one move from this point to this point to this. But what it is essentially trying to do is it is trying to generate the code based on the plan which it made, and that code is then executed on the robot. Okay, so this is something which is again a very recent. So SEICAN, I think SEICAN got published 2023 or early 2024. So it's again very early stages, and it showed like significant good results. Now comes the frontier of the robotics, which is known as vision language action or vision language actuation models. So this is something the research is only happening, I guess, in like 6 companies or 6 to 7 different research labs. So one of the most prominent one is the UC Berkeley research lab, where there is Prof. Sergey Levine. So he also started his company on physical intelligence, which is trying to make this vision language action model. Then there is a good research happening in the CMU in the robotics lab. It started again. So what started happening is because this vision LLMs became so big, so a lot of these professors they started their own company. So Sergey Levine was one of the best prof. So he started his company, Physical Intelligence. Again, I think there is a very good round. Then there's this guy Deepak Pathak. So he was also prof at CMU. Deepak Pathak and I think Abhinav Gupta. So both of them are like IIT Kanpur graduate, did their PhDs from CMU, worked as a prof there, worked on a lot of these robotics pipeline. They made a company as Skilled AI, and yeah, they're also doing pretty good. But so there are these 4 places in the globe, and then there is this NVIDIA Gear Lab. So only those 4 to 5 basically companies slash research labs are working on this. The basic intuition is very simple. The LLM gave us the language understanding, VLM gave us the vision understanding. Now VLA, what it does is it combines everything and it gives end-to-end actuation and action also. Okay, so for example, in this video, basically the example which I have given. So let's say there is this lot of vision data you get for ADAS or like this autonomous navigation. So yeah, again, so there are these robo taxis by Tesla. They also use some form of VLA model. But again, very early stage again. So they have not deployed VLA, but in the testing they are trying to use it. So yeah, so basically you have a lot of vision data, then you understand the nuances or the captions behind those vision data, and you convert that to language. For example, you get this frame level captions, and then on top of it you figure out the action or the future trajectory. For example, where to go, how to go, what to do. Okay, so you figure out here, let's say I have to put more on the speed or more on the direction, and what do I need to do. So this is the basic understanding of vision language action model. But again, so I have told it in the ADAS or autonomous driving scenario, but it essentially just as it is, you can actually copy it to the robotic scenario also. So think of it like these are the models which integrate perception, semantic understanding, and action outputs in an end-to-end manner. Like a single model can essentially take in an image or a video of the robot's environment, as well as a textual command or a goal description, and directly generate the robot actions to execute. Okay, so think of it like these are like generalist robot policies. Essentially, we were trying when we were doing reinforcement learning, it was very specific, but these are like generalist robot policies that attempt to do everything in one model, what used to be broken into different subsystems. Okay, in VLM also we merge a lot of system. In this, though, we merge everything only. So VLA models essentially mark a shift towards more of a unified policy learning, where there's a perception, reasoning, and controls are not separate models, but a part of a single model's knowledge. Okay, which what that enables is it can now make the robot behavior more holistic and context aware. So think of it as if the perception stack is different, control stack is different. Both of them are not getting trained jointly. Like there are some information which is there in perception which is not flowing into the control stack. But now, because everything is jointly getting trained, it is more holistic and context aware. For example, like you can think of it like this, a VLA robot given an instruction to pick up the particular block from one particular place to other place. It will jointly consider the visual scene, where it is, how to grasp it, as well as the instruction semantics, what is the goal state. And then it outputs a sequence of low level actions to accomplish it. Okay. Now the good part about them is that since you are training it in generic way, like you are not considering what is the how does the robot look. So that is not a cross embodiment. Because think of it like this, you don't care about what kind of sensor is getting used. You just need some value. Okay. In robotics, cross embodiment is a very big challenge. Let's say, think about it, there is this version 1 of robot and version 2 of robot. Both of the algorithms which are working in version 1 is not essentially doesn't work out of the box with version 2, because if there is a sensor change or if there is a gear ratio change in the tires, a lot of things happen. But over here, and other thing is, see, it cannot also generalize to, like most of the traditional algorithms, they cannot generalize to cross tasks. Okay. What VLA essentially enable us is, because they use a shared vision language representation, a single model can transfer knowledge between different tasks and even different robot hardware. For example, you learn a concept about fragile objects in a pick and place task. You can just transfer that to a different scenario. Okay, like maybe how to basically place the object gently. Okay, or from one robot arm to other robot arm. Okay, so if the model has seen enough variety, it can do this cross embodiment. Uh, yeah. The other thing is key, you, because it is getting trained generically, you can essentially do a less task specific data and make it more and more general. And because for vision and language we have a huge data sets online, so you can just use it. For example, you can pre-train on internet images and text, so that the world already knows a lot about models. So basically what LLM did for the entire NLP community, VLA can do the same thing for robotics community. Okay. So let's say earlier you used to fine tune each of the things, uh, but let's say now when you have to fine tune, like even these LLMs, when you fine tune on your particular task, you need only very few samples. So similarly, you need very few samples when you have a general purpose huge VLA. You will just train it on your task, very like just simple fine tuning using LoRa or QLoRa or whatever. Okay. Uh, so because of this, now the problem was like you have data inefficiency because of pure RL. Okay. So instead of millions of trials on real robot, now you can essentially do it in like 100 of demonstrations only. So there is this again by NVIDIA, there is this model OpenVLA, which got fine-tuned on a very specific task related to putting the key in the lock, just in an hour of training, because it had pre-trained knowledge. Okay. Then the third benefit which it provides is the robustness. So since you are not decoupling this like system completely, they really can avoid the errors which happens because of compounding of different small models. So your uh, let's say your potential model is 95% accurate. Then there is another model which is only 95% accurate. But when you do it as a whole, so it is 0.95 into 0.95. Okay, which makes it even lesser inaccurate, basically accurate. But because now you're using a single model, the entire accuracy is built within. So think of it like the joint reasoning about perception and action can improve robustness. For example, let's say if a particular object is not at the location where it was expected, VLA might figure out the change in the location and it can replan and essentially get it done. So the end-to-end robustness is much more in this VLA model. Okay. Let's talk a bit about the type of VLA model, essentially the kind of VLA model. So I told you about OpenVLA. OpenVLA is kind of based out of this RT1. So RT1, RT2, these are the robot transformers. Okay. And these were launched by Google. RT2 came in 2024, RT1 came in 2023. Again, very early days of research. Uh, Basically, the key technical trick uh, here is to represent robot action in a format that could be learned alongside language. Okay. For example, here what they did was they encoded the discrete robotic arm motions as if they were robot tokens. So basically, what they are trying to do intuitively is ki, see, like language model, you treat words as tokens. Okay. Vision model, you treat image paths as token. Here, what they are saying is that they will treat joint, basically joint velocities or joint angles as the tokens. So similarly, that's what they did. Uh, Basically, this came by Google DeepMind, uh, and what they try to do is they are predicting discrete action tokens. Okay, how they trained it is, so they use the web scale vision language model pre-training. So there is this Pali X family of vision language models which they used, and then on top of it they did a behavioral cloning by a RL loop. So they used a lot of real robot as well as RL policies to essentially train it. And because these actions are tokenized, the last layer remains unchanged. And model can just learn tokens like opening the gripper, moving from this to this place, all those things. So it's what it is doing is it is kind of generating a sentence, and those sentence you can essentially translate those sentence into the discrete action blocks. Okay. Uh, so basically, what RT2 is trying to do is it is kind of writing a script of primitive moves, ki move left, move up, move by this degree, close the gripper, open the gripper. So it is kind of just outputting frequency. Like think of it, like its output frequency is kind of bounded by how fast you can spell out the tokens. Okay, so it is very good for semantic reasoning, identify what to do, but still, since the tokens are discretized, the motion is still restricted. Okay, versus there is a again by Sergey Levine, this model, the physical intelligence, the UC Berkeley lab, Bear lab. So they launched this model as Pi Zero. The difference between this RT2 and Pi Zero is essentially what it does is it uses kind of a flow matching based diffusion concept, where instead of predicting these discrete tokens, it essentially does it in continuity. So you can essentially think of it, you can do a kind of brush stroke in one go. So you can generate like 50 step trajectory together, and because yeah, so this is how the Pi Zero looks like. So what people are essentially trying to, so now because this is something like Pi Zero, you can essentially tell it in next 50 steps what you need to do. Okay, so let's say earlier we were just saying in the RT2 move to the left, move to the right, basically rotate with particular degree, all those things. Over here, you can just predict the entire sequence only. Okay. So, for example, let's say if there is this open the left door and hand me the spoon, you will essentially show ki this is the, you will just move a bit towards left, a bit towards right, a bit towards left, 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 left. But again, so these are like more of a continuous thing. And as you guys understand, like continuous is better than discrete, and that's why so Pi Zero is kind of the again one of the state of the art models. Uh, Internally, what they are doing is they have again the pre-trained VLM and an action expert, and instead of using the classic diffusion or autoregressive policies, they use a flow matching. Uh, Basically, think of it like, let's say you can do a uh, basically flow matching is something like you can essentially tell the motor to move at a 50 hertz rate or something like that, and you can treat the entire 50 step action chunk as a point. It should denoise along a smooth path. So one integration loop essentially give you the whole motion bus in a few transformer calls, keeping latency as a workable on real robots. Uh, but yeah, instead of predicting pixel by pixel, it is essentially doing an entire stock kind of thing. So that's the major difference between Pi Zero versus RT2. Uh, Besides architecture, so Pi Zero is one of the latest model which is doing. And as you can understand, so it doesn't rely only on the single robot thing. It does a cross embodiment. Then you have the internet scale pre-training, cross embodiment data sets, and then the action expert that you then do a post training. And because of that post training, you essentially can, you see, like it is able to work zero shot in most of the things. So let's say if there is a new task, uh, which it might not even have seen it might be able to do it in zero shot. Plus, you for the unseen task, if you just like, it becomes more sample efficient. You can just provide it very few samples, it is able to learn those things. So that's the basic idea behind vision language action models. And again, so this is the kind of the conclusion slide. Uh, Basically, the timeline versus the adoption and capability. And as you are seeing, again, this is the 2020s. Now it will, the gap will keep on becoming more and more big. Most of the people have already started using AI and deep learning in uh, the robots. In fact, as a matter of fact, we are using AI across. So we are training our own custom VLA models for training the robot. We have our own custom units, bits, which we are using for a lot of things, and they are actually working very good. Like most of the models which we are using, none of the papers were like actually uh, basically published before 2023. So we are actually working already at a very good like cutting edge. And in general, the idea is here. So classical, like if not classical robotics, we would not have reached there. So classical robotics gave us a very solid foundation. Like if you have well-defined repetitive tasks in a control setting, classical algorithms like PID controllers, sense Kalman filters, they are definitely hard to beat for reliability and predictability. But they fall short when environments gets messy or task gets too complicated, that you have to explicitly program it. That's where deep learning is come into basically handy, where we can handle complex tasks where there's a lot of uncertainty, uh, and where you can essentially learn by data rather than relying solely on the what a human can think. So because of this, we can essentially offload some of the thinking to the robot itself, and it will figure out the features or strategy itself, while we define the high level goals or objectives, like what we do in the reward function. And even when we merge a lot of these things, so there are these hybrid approaches where we use a mix of classical and AI, because AI is also not there yet. Again, it's, as I told you, like these are, so Pi Zero was actually launched in 2025, Jan of 2025. So yeah, so again, it's a very researchy field per se. So what we are doing is, again, we have a base of classical algorithms. On top of it, we are applying AI models and essentially using a hybrid kind of scenario